Okay, you can start.
All right, sounds good. So my presentation is called the needle drop rating predictor. I had better names, but they were kind of inside jokes. If you're not like, don't watch the YouTube channel, maybe you won't get them. So kind of stuck with this kind of lame name. So just some background on what even the needle drop is. The needle drop is a YouTube channel emceed by Anthony Fantano. He has over 5 million YouTube subscribers, over like 3 different channels, and 1.23 billion views. He's really famous for his album reviews because he normally is very critical of very well beloved albums. So he's kind of a meme in the YouTube scene. He also, with his album reviews, has a lot of different series, but the series that we're gonna kind of be focusing on is called the Weekly Track Roundup, where he rates singles that were dropped that week and rates them in categories of good, meh, or not good. It's important to note that like even though I'm doing like a whole analysis on him, his ratings, I definitely disagree with him a lot. I just think it was an interesting way for me to get a unique data set by collecting it from YouTube, which I'll get into later. So the objective of my analysis is to compare different machine learning techniques and algorithms, such as the 3 that I'm using here is neural networks, k-nearest neighborhood, and a random forest, using 13 numeric predictors to classify a single song as good, meh, or not good, based on previous ratings that the needle drop has given. So data collection was a little involved. So I used 2 sources. So I used the Google API, which obviously Google owns YouTube. So YouTube is also in there. So the API returns, you send a request out. I use Python to do these requesting because I don't even know how to do them in R. But I requested the playlists, all the playlists in Anthony Fantano's catalog of playlists. And then from there, I took the playlist ID, requested the playlist items, which are the songs. And then from there, I had to create some type of logic to take all the ratings from the description, because luckily you post in the description, or this analysis would be a lot harder to collect data for. And from there, I use the Spotify API to take the artist and the song title and to search it through Spotify. And then once I got a Spotify ID, I use that to get the audio features of the song, which I'll go into what those features are later. And of course, a lot of those failed, just whether it wasn't on Spotify or, maybe it was misspelled. So I did have to manually put in a few through just the Spotify developer console. So the data, I'm sorry it's so small. I kind of just wanted to make sure that everything, if anyone had any questions, I had the information here on the slides. Spotify gives out with their audio analysis acousticness, danceability, duration, energy, instrumentalness, key, liveliness, loudness, mode, speechness, tempo, and valence. Some of these aren't even words. So, that's why the descriptions are kind of important. I'm not going to go through all of them just for the sake of time, but like acousticness is the confidence measure from 0 to 1 of whether a track is acoustic. So, if there's a track that's very much, played a guitar in the background, no no production besides that, it will probably get close to a 1. And if there's no acoustics, you know, very, let's say, electronic production, then it will get closer to a 0. Oh, and this is also important. I was able to get 3,019 observations from my collection. So I split it into a 30-70 split. So a 906 for the test set and 2,113 for the training set. So now that we have the data, I looked at, so which ratings did he give most often? And he gives a good a lot, you know, obviously a lot more than not good or even meh. So that kind of creates some challenges, especially in some of my models, which I'll get into later, on, you know, when a song is actually not good in the analysis, it doesn't necessarily pick it up. And, you know, I even did a pairwise function. I was hoping to see some kind of relation at all, but it's kind of just all gobbled up together, just because there's so many predictor variables and just so much data in general. Another important fact is that the data that I collected wasn't normal much at all. Like it was, you know, kind of all over the place. Like it looks like a needle drop valence looks fairly normal. Maybe tempo was fairly normal, but there were some that were like very not normal, very skewed. So I needed to kind of try to normalize them, especially because some of my models do require normalized data. So for data transformation, I utilize the scale function R, which is honestly a great function. I can't believe it worked as well as it did. It calculates a vector's mean, which is just the column of the data frame, and the standard deviation, and it removes the mean and divides by the deviation. I scaled all the predictors except for mode, because mode is actually, even though it's an integer value, it's 1 and 0. So I didn't want to mess with that kind of, if I would have messed with that, I would have got weird values for mode that are kind of unnatural for the mode, especially because mode is, I believe mode is whether it's major or minor type of scale, which is music talk. I don't really understand it, but you know, I tried to learn as much as possible for this analysis. So first, let's jump into the K nearest neighborhood model. So it looked, so I used a K of 34, and I tested all Ks up until, I don't know, I think it was like 45 or something. And it looked like 34 was actually the most optimal K. And the accuracy I got off the model was 0.5386, which, you know, isn't necessarily the greatest, but, you know, given that there are 3 categorical responses, as in good, met, or not good, 50% chance is a lot better than just randomly guessing one of those. So that's pretty good. But I think one of the more important stats to look at here is the sensitivity. So if you look at the sensitivity, like good is very sensitive, meh is not very sensitive, and not good is like not sensitive at all, which you can kind of see in the data. And that, you know, just is because that meh and not good really didn't have, you know, a ton of data to in each of their categories. When it came to random forest, I did a little worse. Actually, I ran random forests a couple times. I ran all of these a few times, and random forest and KNN were kind of neck and neck. They kept on going back to beating each other, or not beating each other. But each time, the optimal split was 2. So it looked like this optimal split was always 2. And sensitivity is kind of the same deal here. Good has a very high sensitivity, and not good have extremely low sensitivities, which I kind of want to get into later. But I that is affecting my models a lot. And then for my neural network, for hidden layers, I only did one hidden layer because honestly, my computer, the computation of my computer wasn't great. It honestly took probably an hour to run a hidden layer, and it was taking 3 hours or more to run additional layers. And so I wasn't necessarily even able to find the sweet spot, just because of some of the limitations of the time I had and the computation I had available to me. But I did find that 8 neurons kind of worked the best between all the models that I used. And repeats, actually, like when I first started my training my neural networks, I didn't do any repeats. I kind of just did a repeat of 1 where it just goes through it once. But repeating it, I did up to 5 times. Actually really greatly impacted the accuracy of the model. So if we compare the 3 models, K-nearest neighborhood, which I used tenfold cross-validation, the accuracy was about 0.554. Random forest, tenfold cross-validation, about 0.53, basically the same. Neural network, I honestly had a hard time finding a good validation technique. There was a couple that were possible. Even mean squared error, the more research I did, I kind of saw that you kind of needed a binary, and I of course have 3-factor variables, so it wasn't necessarily binary. So I kind of just used the confusion matrix to test accuracy, and through the confusion matrix, I only got 0.48 accuracy on my model using my test data.
Okay, 1 minute left.
Okay, that's perfect. What would I do different? Spend more time training different neural network models. I did neural networks last, so that's what that was about. I'd try to format the data into binary classification or continuous regression, just because that's easier and they're more accurate. And more importantly, find different data, because I don't think this accurately predicts what I want it to predict. So Spotify has another endpoint called audio analysis, which returns a lot of data, and that might be the better data set to use. It was just a little bit much for this project. Thank you for watching my presentation. I really appreciate this semester and everything, and I'm happy to answer any of your questions.
Thank you, Nicholas. Yeah, I think it's very good that you spent a lot of effort to get the data from YouTube. So you use scraping? You mean?
No, I actually didn't
really.
have to scrape. They have open APIs where you just request
open
from
API.
a URL.
Okay, I see.
Yeah.
Yeah, and a couple of questions. So first, you said that you use the training test data, so the training test validation approach, but also you mentioned that the tenfold cross validation in KNN and RAF, the random forest. that
Yep.
is for hyperparameters? What do you mean that you used the tenfold cross-validation?
So I actually used the caret or caret library in R, and it automatically does tenfold, or well, you can kind of it will do cross-validation for you, k-fold cross-validation. I just chose 10. And
not sure, but your result seems the 900 observations, so that means for the test data set.
Yeah, 900.
Right?
Yeah.
Yeah.
Yep,
so
test.
Cross-validation is used to choose the model. What do you mean? You used the both?
Well, actually, cross-validation I kind of used to find the optimal K.
Okay.
And the optimal
and the
splits.
splits. Yeah. Okay, I see. And what procedure did you use for neural network?
What library?
Function library. Yeah.
Neural net.
Neural net for library. Okay, I see. Okay. And for me, so my comment is that can you show the results for neural network?
Are you like?
Oh, I mean just the confusion metrics. Yeah, I think that this looks better than others. So at least for example, for May, the more observations are categorized as May when the truth is May. So, and also the not good, only 9 observations, but the proportion, that may not be good, but at least that group. So accuracy is lower, but the accuracy is just, one measure. So probably accuracy for this is lower because the prediction for good is smaller, the counts for when the truth is good. So that affects the overall accuracy. But it sounds for me that this is more, meaningful prediction. But anyway, it sounds the prediction is difficult, and maybe we have to look into the data or have to find more variables to get a better prediction. Yeah, but overall, yeah, it's very nice to compare 3 methods. Yeah, so accuracy is just one measure. So yeah, if you use other measures, maybe possibly we may get different results. Yeah, thank you. It's interesting. Does anyone has question to Nicholas? No.
Hey Nick.
Yeah, what's up?
So when you were finding your hidden layers, was it just trial and error and seeing which one actually converged?
Yeah, and honestly, I honestly did a lot of research online for this neural network one. I put in a lot of work researching the best practice on trying to find how many neurons to put in a hidden layer. And I honestly was hearing a lot of just trial and error, and that did stink because it took up a lot of time. But I do think I found kind of a sweet spot in my data.
Yeah, I think that you have 13 variables, so slightly less than 13 is good number to start with. Possibly if we have multiple layers, like the first layer 8, second layer 5 or something, possibly it gets better, but yeah, it's hard to optimize that kind of hyperparameters.
Yeah, I wanted to do a second layer, but it literally was just taking like all day, and then an error would pop up, and then you just lost all that. So
yeah, neural net package isn't really fast. So yeah, that's true. Yeah. Okay, so thank you. So maybe we go to the next one. Robert, can you share the screen?
Okay.
Okay. Yeah, you can start.
All right. Hold on. Okay. So my name is Robert, and today I'm going to be analyzing area population on housing data. So to sum up why I decided to do my project on housing data, it's basically because when people construct houses in neighborhoods and such, there's a lot of factors that go into the decision-making of how the house is going to be designed. One of these factors that's often looked at is the population in the area. So if you're a city planner and you want to construct like a residential area, ideally, you're going to want to make sure that everyone in the population has a place to live. So for example, like if you live in an area with a lot of people like New York City, the houses there are going to generally be smaller and more compact so that they can account for more people. But on the flip side of things, if you live in like some rural town in Kansas, having a big farm with a lot of land isn't going to be much of a problem since you don't have to worry about population. So that's just one example of a variable that like relates to population. I want to see what other aspects of a house are also related. So the objectives of this presentation are to create multiple models, both linear and nonlinear, to test the relationship between housing data and the population in the area that the house was built. And then I want to compare and interpret these models to see which of them is the most accurate. So I got this data set off of Kaggle. It contains various housing data for 5,000 homes all across the US. And there's a total of 7 variables, 6 numeric and 1 categorical. And here's a picture of the raw data set just so you guys can get a visual. One thing that's important to note is that for the first 4 variables, these are the averages of all the houses in the area. So for example, like if you bought a house in Detroit, it's going to show the income for what an average house in Detroit would be, rather than like the income for the person who bought the house. As you can see, we've got average area income, house age, number of rooms, number of bedrooms. And then there's area population and price, which these are not averaged out. And then at the end, it's abbreviated, but it has their exact address.
Sorry, the sample unit is town, right? 5,000 towns, right?
Yeah, 5,000 homes, 5,000.
5,000 towns, right? So the each line is the average of the houses in town, right?
Oh, correct. Yes.
Right. Yeah, just to make sure. Yep.
Yeah, sorry about that. Observations 5,000. It would be out of each area. So I had to make a few modifications to the data set to make it easier to analyze. The first thing I did was get rid of the address column because it's irrelevant to the data. Although you could make it relevant because they did have state and zip code in there. So I think it would be interesting some other time to potentially group them by location. But regardless, I also changed the variable names to make them simpler. So keep in mind that for the first 4 variables, it's the average household in the area, not the actual house. So moving on to the actual analysis, there's 3 different types of models that I created to predict the data. The first was a linear regression. I also made a GAM and a random forest model. So in order to measure the accuracy of these models, I split the data into a 70-30 split between the training and the test observations. So the training set has 3,500 observations, and the test set has the remaining 1,500. These observations were randomly chosen to ensure that the order that they're listed in doesn't affect the results. And the test MSE is going to be used to compare between the models. So the first model that I did was a linear regression. You can see we've got population as the response variable, and the rest of the variables are predictors. You can also see that the p-values for almost all the variables are statistically significant except for bedrooms. What's interesting is that I ran both backwards and forwards stepwise selection models just to see what they came up with. And they both generated the same model as the original linear regression with all the variables in it. I also checked to make sure that the assumptions of a linear model were not violated. So you can see that the VIF for the variables, each of them is below 5. And the error terms don't appear to be correlated. I don't know what that blob could be else. So the next model that I created was a GAM. I have all the variables placed into a formula. However, I ran a correlation matrix before, and I saw that population and price, they both had a decently strong correlation with each other. So I added a smoothing spline to the price variable. And you can now see that the p-values, they appear to be higher compared to the last model. This time, there's only 3 variables that are considered statistically significant. And then the last model that I ran was a random forest. So because there's 5 predictors, I set the M-try to 5. And you can see that the mean of squared residuals is pretty large at 40 million. So looking at the test MSCs for each of these models, they're all really, really high numbers, but the lowest of the bunch is linear regression, so that one is the winner. So in conclusion, as we just saw, the linear regression is the best model of the three. And in the future, if I had more time, I would have liked to implement other models such as like SVMs to see how they would do. And I also think it'd be interesting, as I said earlier, to group the data by like their state or zip code for location and see if like that could be a relevant variable potentially. But that's all that I have for my presentation. So thank you very much.
Thank you, Robert. Yeah. Yeah, I think it's a little surprising that the population is explained by, you know, the average age or the average the year of the house. I think that, you know, those are not logically related variables, but it's very significant. So I'm not exactly sure what's happening, but yeah, I think it's interesting. Yeah, and MSC is squared quantity, so always it's large. So the root mean square error is probably easier to interpret, right? So because we have the y minus y hat, then unit is, okay, so a person, then we take square, so the unit is person square. So finally, if we take square root means square error, then number gets smaller and the unit becomes person again. So it may be easier to see that what it means. So if the square root of MSC is, for example, the I don't know, the 1000, then that means that on average the error in predicting population is 1000 people. So that may be easier to interpret. Does anyone has a question? Question to Robert?
Yeah, real quick, could you, I think in your linear regression, it said the number of bedrooms wasn't significant. Was it the same for the GAM?
I can double check that. It was 0.0976 here and then 0.0037. So it was statistically significant in the GAM.
Okay. I don't know. I just feel like if you have more bedrooms, you have more people. So I don't know. I guess
yeah,
the professor kind of said it already. So
yeah, it might be like
okay.
with the averages or whatever.
Yeah. Okay. Thank you.
Any other?
What year? Oh, sorry. What year was this data collected from?
There was no year listed, unfortunately.
Okay.
Do you have any other questions? Okay, then go to next. Arif, can you share the screen?
Sure, yes.
Okay, you can start.
Okay, hello, my name is Arif, and I'll be presenting my project, which is on predicting wholesale customers. Starting with a brief introduction. So this data was derived from the UCY repository, and it's called the Wholesale Customers Dataset, of course. And the data was collected in Portugal and published in 2011, which seems pretty long ago, but it's not too outdated, I guess. And there are 444 observations in this data set, and it consists of 8 variables. And from these 8 variables, I actually dropped one of them and added my own. So we're back to 8 again, as I'll show on the next slide. So here, the response variable for this data set is called channel, or these are the type of customers which can be either HORECA, which stands for hotel, restaurant, cafe, or it could be retail. And this is a binary, and of course it's categorical. And there are Also, there were 6 original predictor variables, which were fresh, milk, grocery, frozen, detergents, paper, and deli. And all of these represent annual spending in each respective category, and they're continuous. And I also added one of my own variables, which is the percentage of spending on perishable items. And these are the ones with shorter shelf life. And I thought this would be important because restaurants and cafes and maybe even hotels would spend more in this category compared to retail, which might lean towards products with a higher shelf life. So the non-perishable items like detergents, paper, grocery, and maybe even frozen. So the objective will be to compare various classification models to determine which would be best for classifying wholesale customers into either HoReCa or retail based on their purchases. And the plan for my analysis will be to build 4 models for logistic regression, LDA, QDA, and K nearest neighbor. And the comparison will be done based on their prediction accuracy. And for the prediction, I'll be using 80% of the data for training the model and 20% for the test. I'll also be comparing the area under the curve. So here I have the pairwise plots, and it might be a lot to process, but for one thing I have to mention is for the channel and detergents paper, you can see that all the black dots representing HoReCa are grouped to the bottom left, and the red dots representing retail are further to the right and spread out, indicating that retail customers actually do spend more money on detergents and paper. And similar can be said for grocery as well. All the black dots are grouped towards the bottom left, and the red dots are further to the right. And also there is a positive correlation between grocery and detergents underscore paper, saying, indicating that both of these are likely to be significant, as we'll see in the next slide. So here I ran my logistic regression, and upon running this, other than the intercept, there are 3 other significant values here. First is grocery, and second is detergents, as well as the variable I created, which is for the percentage of perishables. And looking at the coefficients, it seems that with the higher spending in grocery and detergents, actually the retail customers are more likely to spend more money on grocery and detergents. And yeah, so other than that, after running the model and testing it, the accuracy was 56.82% and AUC was 51.34%. These are not that great considering it's a binary classification problem. So I tried the LDA next to see if there was an improvement. So using the LDA, I was able to get an accuracy of 85.23%, and the AUC in this case was 83.71%, and this was a significant improvement over the previous one based on their accuracy. So after this one, I also tried the QDA, which was also an improvement over the logistic regression as well as the linear discriminant analysis. And this one had an accuracy of predicting 88.64% of the customers correctly and had the AUC of 88.39%. So next, I did the KNN. For this, this one was better than all of the previous ones, and this one achieved an accuracy of 92.05% and AUC of 92.41%. And for this, actually, I just selected 10 as K. I didn't really do any cross-validation. So this could be even better if it's cross-validated, I'm assuming. And finally, to compare all these models, it seems that logistic regression performed the worst, and LDA and QDA performed much better, but the winner here was the KNN based on its accuracy and AUC. And to conclude, So it seems that based on the models I compared, KNN had the best performance, maybe not in terms of speed, I guess, but in terms of accuracy. And the results, so in the future, the results could be even better if the K was optimized, and also, actually, I tried it with the K equals 20 and 21, and with those I got it fluctuated. So first time I got 94%, then I got 95, and both of which are better than the 92 that I got with the K equals 10. But anyway, so these findings may be useful for marketing purposes, for advertising, or I guess placing products to target whichever customer you're interested in targeting, and also maybe even recommendation systems and whatnot. And that is all. Thank you for watching my presentation.
Thank you. I think it's good that you compared many methods, and the one surprising, results is that the LDA, QDA, KNN are much better than logistic regression. Logistic regression is basically similar to LDA in terms of, in the sense that both have the linear discriminant, the discriminating boundary. So I wonder why that happened, but yeah. But the LDA, QDA, KNN, it worked good. Yeah. And also, sorry, I think that yeah, Nicholas, the Nick's presentation, they standardized the variables, right? So that may matter for KNN because KNN uses distance. So if you standardize it, maybe you get possibly different results. So those are my comments. These. Okay, so do you have any question? Does anyone question to Arif?
Maybe you mentioned this, but how did you get that other column that you added? That was percent perishables.
Actually, I did not mention it. Thank you for bringing that up. So for that, it's essentially the sum of fresh milk and deli over the total, and it was in the decimal form.
Okay, got it.
So you created this variable, or?
Yes, I created.
Okay, I see. Yeah, that makes sense. Yeah. Okay, do you have any other questions? Okay, so if not, then we go to the next one. So Connor, can you share the screen?
Yeah. All right. All good?
Yeah, you can start.
Okay. So hi guys. My name's Connor Fox. I go by CJ, and my project is on breast cancer recurrence. So just kind of starting off with a little bit of background. It's that annually in the U.S., more than 230,000 women are diagnosed with breast cancer. So I'm sure a lot of us maybe even know someone or know someone who's been affected by breast cancer, or have been affected. And so I thought it'd be an interesting topic to kind of take this project with the objective of applying some different models to try and predict whether or not a breast cancer patient will have a recurrence event, meaning that like a patient who's been diagnosed with breast cancer will later have more breast cancer, or like returning cancer. So just to describe the data, I got this from the UCI machine learning repository. It has 286 observations of people who are diagnosed with breast cancer. There are some missing values in there that need to be handled. And then it has a classification variable, which is recurrence or not recurrence, which is just kind of, tells whether or not they did end up having a recurrence event for their cancer. And then each patient also has 9 characteristic variables at the time of their diagnosis. So Age is how old they were when they were diagnosed. Menopause is whether they were pre or postmenopausal. And then some information regarding their cancer. So the tumor size, there's these nodes and node caps that are characteristics of their cancer, a degree of how malignant their cancer was on a scale of 1 to 3, with 3 being more malignant. So, kind of more threatening. And then breast and breast quad give the location of where the cancer was, and irradiation tells us whether or not they received radiation therapy to treat their cancer. So I had to do just some minor pre-processing for the data. So I just removed observations with missing values. So I ended up with 278 observations after that. So lost about 8 observations. And then other than that, I converted the recurrence, non-recurrence, the response variable to 0 or 1, so that I could apply my models to it. And I also converted the characteristic variables to factor variables, because although one of the variables is age, but it wasn't given like their specific age. They were basically divided into certain bins. So you had people were classified as being, age 30 to 39, or they were 40 to 49, 50 to 59, so on and so forth. And that's just kind of how all of these were. I didn't actually have any continuous variables. So I converted everything. They were originally like character variables or whatever. I just changed them all to factor. And so just kind of to conduct my analysis, I started off just choosing my predictors with backwards deletion. So I would just did logistic regression on all the predictors and use backwards deletion to just choose which predictors I'm then going to use in each of my models. And then I'm going to apply the models with cross-validation. And the models I'm applying are logistic regression, LDA, ANN, and then using support vector machines. So choosing the predictors, like I said, choose them by backwards deletion. So getting the model with the lowest ACI. And this just shows the predictors of menopause, node caps, degree malignance, and then irradiation, which all kind of makes sense. Node caps, I believe, is I'm not exactly like 100% sure on like what that means. The description of that variable was about just kind of how the cancer cells like breached in their body. I'm not 100% sure on the science all behind that, but it does generally make sense. So since all of my variables are factor variables, kind of the best way I could give just some preliminary like description of the data is in these tables. So we can see that when somebody having a recurrence event of their cancer is kind of more likely as we have the degree of malignance, which is in this top table. So as we get higher up, like 3 being a more malignant cancer, we see that we kind of have a greater proportion of there being a recurrence event. And then same with postmenopausal. So in the second table, we have G40 and LT40, which are postmenopausal. I'm not 100% on what the difference is, but I do, the pre-meno is if the patient was premenopausal. And then node caps being present in that third table. Again, we have greater proportion of there being, recurrence events. And then for some reason with radiation treatment, if they did receive radiation treatment, there are more recurrence events in that category. But now just kind of, for actually applying the models, I just did 5-fold cross-validation using the built-in function in R, that CVGLM, where I just defined the method to calculate the error, but then that does all the kind of heavy lifting for me. I got a mean for cross-validated error. I got 0.25, standard deviation of 0.013. And then for the other models, it was a little bit more involved. So for linear discriminant analysis, I had to write the implementation myself for doing the cross-validation. So I started off just randomizing the observations in the entire data set, split it into 5 subsets. And so we trained the model with 4 of them and then used the 5th as the test set. And we do that 5 times until each of those 5 subsets are used as the training set. And then I repeated this 10 times. So when we get the errors for after each subset has been used as a test set, I would take the mean of that, and that would be my cross-validated error for that time, and then I would do that 10 times. And then taking the mean of those 10 values, I get a mean error of 0.25, a standard deviation of 0.011. And then did the same process for doing KNN and get some really similar values here. I don't really have a whole lot of improvement here with 0.25 is my mean error, and then standard deviation 0.008. So I do have some slightly smaller standard deviation. And then I tried to do some support vector machine. And so for doing this one, I use the same cross-validation method, like the same implementation for it. But I did tune the model to try and find the best parameter for cost. And so using the tune function in R, it picked cost of 1. And then used that optimal model with that cost value to then do the same 5-fold cross-validation 10 times. And surprisingly, it actually did significantly worse here with the mean of 0.42 and standard deviation of 0.02. So just to kind of summarize here, we do have KNN with the lowest error. Marginally, it's not much smaller than LDA and logistic regression. And KNN does have a bigger standard deviation, so logistic regression, LDA, and KNN all perform pretty similarly. And support vector machine does perform the worst out of the models that I applied. And so just kind of some future improvements that I think I'd do is kind of explore some models by different criteria. So obviously I used AIC to pick what predictors I even used. So maybe exploring some different ways of picking predictors and things like that. And then also kind of exploring further with SVM, just because I'm not entirely sure, for what reason it would perform so much worse than the other models. So I think given more time, I'd like to look more into that. But that's all I got for my presentation. So thank you for listening, and any questions I can handle now.
Thank you, Connor. So can you remind me what are the predictors? You said many of them are categorical, but some continuous ones?
No, there actually were no continuous ones. So when
I see.
So they were all kind of read in as character. So I just did them as factor, because even though we do have some that would, you would think would be continuous, like age, all of them were separated into like bins. So in the data set, if a patient was 32, they were just the value that was assigned to them was 30 to 39.
I see. So support vector machine is a method to classify the categories when we have highly nonlinear relationships. So maybe the absence of continuous variables may matter for support vector machines performance for this specific problem. That may be a possibility. Yeah. So what kernel did you use the support vector machine?
Linear.
Linear. Okay. So then maybe it's just isn't different from the linear based model like LDA logistic. Okay. Does anyone has questions to Connor? Yeah, I think that it's the fair comparison of methods by all cross-validation, 5-fold cross-validation. So cross-validation is good. At first, one, we have larger training set, and two, each observation is tested just once. Each of the all observations are tested just for once. So it has less variability. And so, yeah, I think that generally the cross-validation is good to check the test performance. Yeah, validation approach is also fine, but usually it's used for special cases like time series or yeah, something like that. Okay, so does anyone has a question to Connor's presentation? Okay. Then maybe we go to the next, the sheep. Can you share the screen?
Yeah, I'm just making sure everyone can hear me. Can everyone hear me?
Yes, yeah.
Okay.
I cannot see your video, but I can see your voice.
Sharing right now. Can you see it?
Yes.
Okay.
Yeah, you can start.
Okay. Hey everyone. My name is Shiv, and I'm doing my analysis on the diamonds data set. Just kind of as an introduction here, diamonds have existed as a commodity as far back as humans have existed, but recently they started becoming popular in the 1800s. And it's kind of important to make this analysis because you can kind of draw the analogy between predicting diamond prices to predicting stock prices because it's a commodity. So there's two main targets that we can predict that people predict with this diamonds data set. And one is being price, the other is carat as classification. The goal of my presentation would be to examine the different pros and cons of the different learning methods we learn in this class. The methods that I aim to predict the price with is linear regression, multiple linear regression, random forest, and then lasso and ridge. This is the table of contents, kind of what my presentation is going to be structured like. So first we dive into the data description. Diamond's data set is a pretty clean data set. It has roughly 54,000 rows. There's 10 different variables and no missing values. Over here on the right, it can kind of tell you what each predictor is and why they're important. The price is going to be numerical, the one that we're predicting. Carat's going to be also numerical. The next three here, cut, color, and clarity, are all categorical variables. Then the rest of them down here, X, Y, Z, and then depth are all numerical as well. Depth is important right there. It's different than 8 and 9 because of that little calculation kind of combines them. And then again, the source is Kaggle, but Kaggle originally got this data set from Tiffany and Co.'s snapshot price list in 2017. That date is also kind of important. You'll see in the data. So this is the kind of the correlation plot that my data has. It's important to notice the noise and the positive correlation. You can see the positive correlation in carat in price, and then also in X, Y, Z in depth in price. And that kind of gets kind of intuitive because the price of it will kind of depend on how big it is, right? So originally you don't see much of a correlation with the categorical variables that you see there, cut, color, and clarity. And that was my first initial impression. But as you can tell in my other models that I'll show you in just a second, I was actually wrong about that. So pre-processing, the pre-processing I had to do for linear regression was actually kind of different than the other models. That's because outliers and non-homoscedastic data, which is kind of very spread out data, highly affects linear regression. So what we did, if you notice, the data set stops at a certain price. So the prices that you see after those higher carats in the bottom left graph after 2.5, those are kind of just considered outliers. So what I decided to do was just to filter the entire data set and cut everything out that has above 2 carats, just because that would be outliers anyway. In a sense, just removing outliers. So this is the pre-processing that I did with the other models. For random forest, there's no need to scale the data. There's only the need to convert our categorical variables into numerical ones. And so that's what I did. I converted color, clarity, and cut into numerical variables as I think it was an as integer function. And then you can see the new data set that I'm working with on the right. And then for these methods that I'm training, the random forest, lasso, and then ridge, I split the data into test and train. Moving on to methodologies. This is just a picture. It has nothing to do with my presentation. So the first one we can start off with is here linear regression. I've already told you that as a part of pre-processing, I filter the data, which is very important. You'll see in the results. So the goal with all of my linear regression models was to optimize the parameter list and come up with the best result. So first I started where it's kind of obvious to start, which is with the predictor that's most highly correlated to the price, which I saw that it was carrot. So I made a simple linear regression model modeling the price based on the carrot. And these are the results that I've got. That result is over there on the left right here. So the data doesn't seem really linear, and you can see it's kind of exploding. There's no clear like identifiable pattern. That's not what I wanted to see. I wanted to see more of a tighter fit. Over there, I reported the AIC and the R squared of our first model. Next, I thought to myself, how are we going to condense the data? And I thought of taking the log of a log transformation of both price and carrot. So I did that, and I received a lower AIC and a lower R squared. The chart looks better. There's kind of a pattern that you can kind of make out, but it's still not what we want to see. My last attempt actually ended up being the most accurate of what I wanted to do. And this was interesting because remember how in the beginning I said that cut, color, and clarity didn't seem important to me. But after trying some different parameter lists, I found that taking the log of price and predicting it with the log of carrot, cut, and the categorical variables as numerical variables turned out to be the best result. That's the graph over there on the right. And then you can see the AIC reported, and then furthermore towards the bottom, you can kind of see the R squared value and then the mean squared error, like after implementing with the test and train data set. So moving on, we're gonna try the lasso regression here. And then for lasso, I'll be including all of the features in the regression formula. So it's not just so a select few, it's kind of all of them. I chose lambda to be 1. And then after calling the model and cross-predicting with the data set, these are the results that I've got. If you look at the graph here on the right, you can see that my model wants to predict all the carrots above 3, 4, and 5 to be a much higher price than they actually are. And this is actually doing its job correctly. It is correctly predicting the price, because if you imagine their home kind of like crowd for the observations above 3 carat, it would be a much higher price. It's just that the data set that I'm working with cuts the price off at a certain limit. And so this kind of skews the result. Also, that's kind of another thing I wanted to note, is that I did not filter the data for Lasso, Ridge, and Random Forest. So moving on, the next kind of model that I implemented was Ridge regression. Again, I also converted the categorical predictors to numerical. And then after splitting the data and choosing lambda to be 1, I called the model on the train set and cross-referenced it with the test set to produce this output. You can see on the graph that it looks like a tighter fit. It seems that the prices are being more like predicted accurately. However, this is actually interesting to see that this kind of performs slightly worse than Lasso, which was surprising to me. Finally, the final data, the model that I implemented was Random Forest. Random Forest did not need for the data to be scaled. And then for my implementation, I chose the max nodes to be 15, and I chose the tree to be 8 splits. And I found this data to be better than the standard 10 split that we usually do. I did not implement any K fold cross validation to kind of determine the optimal split, but this is kind of just a trial and error. I've tried a couple different models and found that this would be the most optimal number of splits. Over here, I'm predicting the price with the other variables that are in the data set. And you can notice that the graph looks much better with random forest. It's kind of, I would like to say that it's the best that we've seen so far. The R square value, you can see over at the bottom. And then the mean squared error compared to the other models also seems to be a little bit better. So those are my models that I've implemented. Now I'm going to kind of just show you the table for the results. Over here, you see up at the top, linear regression is divided into two categories. The top one is going to be just the predicting the price with caret, and then the one below that is going to be the log transformation. And then if you notice that the multiple linear regression and the bottom row for linear regression, the data points kind of like differ from the rest of the table. And I think this has to do with the fact that I took the log transformation. However, I can't really explain the difference in the mean squared error there. So this is the result. We're going to move on to the conclusion. So overall, the diamond set's really clean. So it's kind of interesting to see which model comes out on top as the best. And I found that multiple linear regression was actually the best. And then random forest coming in at second. It's important to note that I think linear regression up there was better because I filtered the data set. So maybe if I had filtered the data set with random forest, it would have turned out better. So in the future, given more time, I would ideally like to use k-fold cross validation to determine the best lambdas. And then I would also like to implement some sort of dimension reduction to kind of see like what we can get rid of in the predictor set. In this case, and for this entire project, I predicted price given the other variables. However, there's plenty of people who predict other things in the diamonds data set, for example, carrots. And they do that as classification though. So that kind of would have been interesting to explore as well. In the future, I want to implement SVM and neural network. I know that it's probably not optimal to implement neural network with this data set because it's more, you can apply it in better situations. But I want to learn more about neural networks and see how it would look applied to this data set. That's my presentation. Thank you.
Okay. Thank you, Shiv. I think that this has a lot of implication for the data competition, such as Kaggle. I think I think originally the data is from Kaggle, but okay. So can you show the maybe the linear regression results? I think the two residual plots are side by side. One is for original scale of price, and the other is log scale of price. Yeah. Right. No, linear regression result. I think the yeah, this one. Yeah. And the left one is the original scale, and right one is the log scale. Correct. And yeah, so the yeah. So at first, when we change the scale, then the results such as R square or AIC or mean square error, those are not comparable. You mentioned that, but it's not comparable. And that is a big issue in data competition. So in data competition, there is some specific measure, maybe MSE in original scale, we want to do best. So it's not comparable. That is the one thing we have to be careful. But as you show the graph, then right graph looks certainly better. Left one has more heteroscedasticity. We have larger variability in residual when predicted price is larger. So that's not good. But the right-hand side, more random. We have some pattern, but that is based on some truncation, maybe some truncation, the censoring of the data, or maybe some observations, some variables are not entirely continuous. Maybe we have some discrete, it can only take some discrete values. So that is the problem. But basically the right-hand side is more random. So if the residual plot is more appropriate, then the model is more likely to be appropriate, so that you can go for it. So that's the thing. And also, can you show the table which compares all methods? Maybe. And as mentioned, the MSE or R square, even R square, are not comparable if you transform the variables. And
so the disparities that I'm seeing between the linear regression models is because of the log transformation.
Yeah. So if you wanna compare, then basically you have to go back to the original scale, then you can compare MSE, and maybe R square also. That's true. But anyway, and the MSE, so, and probably this is hypothetical claim, but if you use MLR for original scale, the probably MSE is better than rich or Lasso regression, because the multiple linear regression optimized for MSE, so usually it's better. Of course, the test performance, so it's not really the 100% sure, but often that's better, especially for the small number of variables. So it has some theoretical foundations, and if we have large number of variables, often rich or Lasso work better, but the small number of variables, usually it works. MLR works better, even if rich or Lasso have more fancy features. That's it. And random forest. Okay. I think that it's good. The random forest usually without any optimization usually it perform worse than the linear-based models. But here it's comparable. So I think you got a good result.
Right.
Yep. And just announcement. So I'm running the directed study with the Antarang for the data competition this summer. So if you are interested in, you can join. You can register for credits for Mass 5990. So probably it will be counted if you are getting the math-related degree. So just let me know. So we have probably weekly meeting, and each meeting that I would like everyone to share their progress in 1 week for the data competition. And the prerequisites are 58-20. So all of you satisfied the condition. Yep. Sorry, does anyone have questions to Shiv? Okay, so I have just one quick question to Shiv. So do you know what is carat? What's the definition of carat?
I honestly, it's the attribute of the diamond that makes it more rare than the other diamonds, but I can't tell you physically what the difference between.
Yeah, actually, I searched on the internet, and the carat just means 0.2 gram. So I found that the people in jewelry industry is really smart and artistic to create a word carat. Okay, so when we say the half carat diamond, it sounds very precious or something, but just that means 0.1 gram diamond, and probably it affects sales.
So it's a measure of weight. Okay.
Yeah, just the different word for 0.2 grams.
Oh, okay. Thank you, Professor.
Sure. Okay, so that's it for the Shiv's presentation. So last one is the Schreier. So the Schreier, can you share the screen?
Yep. Give me a second.
Sure. Oh yeah. Yeah, now we can see. So yeah, you can start.
Okay. So, hi everyone, my name is Shariah, and I'm doing my project on house price prediction in Detroit. So, a brief introduction. Between the year 2014 and 2020, the average home values in the city of more than doubled. It's the most robust growth in the nation. And this is reported by Detroit Land Bank for the city of Detroit. And the way I sort of got introduced to this data set is through canvassing. I used to canvass for Quicken Loans, and we used to tell Detroit homeowners about foreclosure programs, so to prevent them from homelessness. So I found this data set quite interesting. So it is really necessary to predict prices in Detroit houses for homeowners and also for people who are trying to buy or sell houses. The purpose of my project is to find the best model to predict the price of houses on sale in Detroit, and I'll use multiple linear regression for that. So I extracted the data using an API from a website, and originally I had 1,485 observations and 117 variables, and this all came in a CSV file. For data processing, so this took a lot of time for me. So first I started by looking at the data, and I had some points that are not Detroit. So I checked for points that are not Detroit and sort of removed them. And then I renamed some columns, and because I had like unwanted columns, like columns with no input or something like the address, I also deleted those columns. And you might be wondering why I have so many variables. It's because I had numerous variables with the name photos, and these variables had either links or blank cells. And so I converted the blank cells, blank spaces to NAs. Then I assigned, if it was an NA, then I assigned 0. And if it had a URL, then it was 1. And that helped me sum the rows of photos. And I made a new variable with the summation of all photos and deleted all the columns of photos that were unwanted. And after that, I omitted all NA values and filtered the data so the price, bedroom, bathroom is all greater than 0. And I did that just so, because I don't think anyone wants a house with no bedrooms or bathrooms, and obviously houses are more than $0. So that left me with 1,255 observation and 9 variables. The variables are price, zip code, latitude, longitude, the built year, bedrooms, bathrooms, photos, and square feet. So the methods I'll use are, I split the data in 80% training data and 20% test data. I use multiple linear regression, and I also use quadratic terms to latitude and longitude. This is the square feet with price, and as you can see, it's very weak, the relationship. So and this is the one with log on square feet and price. And this is a correlation plot for the training data. And one thing I noticed here is that bathrooms and bedrooms, they're highly correlated to square feet. And I kind of think, well, it's probably because bedrooms and bathrooms kind of represent the area. So maybe that. This is the model 1, and this one is fit without any logs, or it's just a simple one. And the adjusted R squared here was 0.65. This is model 2, where I fit the model with log for price and square feet, and the adjusted R squared was 0.53. And this is model 3. This is the one with latitude and longitude interaction. And the adjusted R-square was 0.11. So in conclusion, model 2 worked the best because it has the lowest AIC. And I think I think in the future this could improve using more methods, maybe dividing the data sets by zip codes and then using more methods, or in general comparing with other models like KNN or something. And that's all for.
Thank you. Oh, still keep sharing screen.
Oh, okay.
Yep. Yeah. Sorry. Can you show the model 1, 2, and 4 again? Model
Sure.
1, the price on. Okay, so these variables. How about model 2? Model 2, logo price 1. Okay, and model 4.
Well,
3. You said 1, 2,
yeah.
3. Okay, I see. And actually, model 2 and 1, 3 are not. Sorry, the AIC of these 3 models are not comparable because the model 2 have different scale for response. So we have to make the scale back to the original, the price. Then maybe you can compare MSE or R square or whatever. So that is probably appropriate analysis. And I think the model 3, you can see that the interaction term is highly significant, the latitude, the longitude, the interaction. And the other 2 may not be highly significant, but somewhat marginal, like 0.07, marginally significant. And what's the sample size? 1,000? 1,000?
1,255.
255. Okay, yeah. Then I think probably, possibly it improves the model a little bit. And I think that if you do fair comparison, I think that the model 3 has slightly better test performance. So that is my guess. And she introduced your quadratic terms. Basically because the geographic information is usually the distance is most important. So quadratic terms works. For example, suppose that the price contour is ellipse, then maybe tilted ellipse, then that should include x squared term and y squared term and xy term. So usually it improves. And in the past, one student analyzed the Taiwan's house price data. That is, I think, on UCI. And he also found that the quadratic terms are useful. So that should be useful. So again, this is good indication that it's nice that they make a scatter plot and the log of 1 plus price that looks better than original scale, and that is, I think, the correct finding. But if you want to do fair comparison, you have to get back to original scale. So that is kind of messy. So that is another reason that the nonlinear model is so popular. So often some curvature can be solved just by transformation. Why we don't do transformation? If we change the scale of y when comparing more than 2 models, more than 1 models, it's really complicated. So sometimes we want to keep the original response variable and do all kind of nonlinear model to overcome the nonlinear relationship between variables. So that is another reason that the nonlinear models are popular. Yep. Okay, so does anyone has question to Shreya? Yeah, I think that it's good that you download it from the Zillow website. So it's not ready made and it needs a lot of cleaning. So, and sorry, did you use the number of photos as predictors?
The photos?
Yeah, photos.
Yeah, so I use their numbers.
Can you show the result, maybe regression results?
For photos?
Yeah, photos, it's included or dropped?
No, I included it, but for model 1, it wasn't very significant. I remember year built and
I see.
Sorry, it's not there.
Sorry,
but,
the model. Sorry, model. Okay, model
Which one?
2, sorry, model 2, yeah. Photos, okay, so it becomes significant and positive, so
Yeah.
that means more photos, higher price.
Yeah.
Yeah,
But
I see. Yeah, maybe professional photographer takes photos. So if you are selling houses, taking a photo takes just a few seconds. So upload as much as good photos. So that is one indication. And the most findings are, I think, consistent with the usual usual finding. The bathroom has very significant positive coefficient because the bathroom, it costs much to install. We need the water pipes and the drain pipes and so on. So it's more expensive. And square footage, of course, it matters most. But the bedrooms has negative coefficient because given the same square footage, more bedrooms means the less equipments. So usually price is lower. And the zip code, okay, so Wayne State has 48202, so that zip code has negative coefficient, so it's not good. And I don't know why, but yeah, some significant factors. Oh, okay, so too many factors, so you just skipped several ones.
yeah.
Right, okay, I see. Year built, positive. Newer house, higher price, so I think it's reasonable. Yeah, it's very important to interpret each coefficient, especially sign of the variables. Yeah. Okay, so that's good. Does anyone have questions to Shreya?
I have a question, real quick.
Go ahead.
Yeah.
So I maybe missed this. Is the price the list price or how much it's sold for?
It's the listed price.
Okay.
So
Do you-
they're
was
all
Listed
on
price?
sale.
Okay.
Yeah.
Was it available anywhere for any of them?
Yeah.
that-
This is from Zillow, and I use an extractor, so I don't think you can find the file, but I have it also. But these are like the listed price right now.
Listed
on sale
price,
from
so
Zillow.
I
Yeah.
see.
So it's not necessarily how much it's sold for, right? Okay.
Yeah.
All right. That's interesting. Okay, thank you.
I see. So sorry, I have another question. So you use the Zillow API to download the data, you said, right?
Yeah.
Yeah, and is there any limit? Like you can download up to 10,000 per day or something like that? Have you ever?
It took a while. I didn't need to because I specified that I only wanted Detroit data, and I guess it worked.
So you haven't ever noticed such limit? Okay, I see.
Yeah.
And the list price, the not sales price, but it's more, current, right? So yesterday, maybe 2 days ago, maybe the most famous the real estate indicator is S&P Case-Shiller index, but that index, yesterday they released the stats for February, so that means 2 months ago, right? And the S&P Case-Shiller uses 3 months average, so that means the 1.5 months delay if we take the 3 months average, right? So 2 months delay already, but the 1.5 months more. Then sales date and the list date is usually 1.5 months difference. So that is basically 5 months old statistics, so very old statistics. So the using listing price in Zillow is very useful to analyze the data. Of course, more noise, but yeah, you can list your home at $1 million. So it has more noise, but yeah, it's good that to use the recent data, most recent data. Okay, so that's it for every presentation. So I will upload one quiz, which basically asks you which is the best presentation, which is the second best, and which is the third best. And you shouldn't vote for your presentation, even if you think that you are the best. US are the best. US is the best. Yeah, and just make sure that they submit your slides today. And also calls. Calls are less important, but the calls, the URL code doesn't have to be very beautiful, but just show some evidence that you analyze in this way. Okay. And a vote for best presentation today. Yeah, and I think that's it for today. And